electricity. We're going to talk about some of the fundamentals of electricity. So radios are powered by electricity, and radio signals are formed from electrical energy. So it makes sense. I mean, you got a radio, right? It's got to be powered by something, and it's going to be powered by electricity. As we talked about last week, we've got those radio signals that are going out. They're formed from electromagnetic waves that go out on that sine wave. So as long as we have a basic understanding of how we control electricity, that allows us to really operate the radios. We understand how to install them. We don't need to, be an electrical engineer by any stretch of the imagination, right? But just kind of a basic understanding will help us as we work with the radios.
Is still out there.
Now, as we think about electricity, electrical charge can be positive or it can be negative. Now, opposite charges will attract each other, and the opposites will repel, just like on a magnet, right? You ever played with magnets and you put the two plus positive sides together and it repels, right? What happens when you turn the other one around? Right, exactly. It comes right together. So, electrical current is the flow of electrons. These are all these little particles, right, that we can't see. But these electrons, they're floating around. These are negatively charged atomic particles. And when you have an atom, these are what usually surround the atom. Okay? So we have protons, which are positively charged nucleus of that atom. And then there are neutrons, which are neutral charged. They have no charge, right? So you got electrons that are negative, you got protons that are positive, and then you have neutrons, and that makes up an atom. And electrons move in response to electromotive force, and they can move independently of the atom. So they can move all around, those electrons, and makes them very useful when it comes to getting electricity going. So we'll cover some more of the basic electrical concepts. So current. This is the movement of the electrons, and it's measured in amperes, notated by the capital A, and it's measured by an ammeter, and it's represented by an capital I in formulas. So whenever you have a formula that is involving current, it's represented by a capital I. Now when we get to talk about voltage, voltage is the amount of electromotive force, or EMF, and it's also called electrical potential. So, we've got this current out here. It's got potential to move. We have to apply something to it to get it to move, and that's where voltage comes into play. And so voltage is measured in volts, notated by a capital V, and it's measured by a voltmeter. And it's represented by an E or a V in formulas. And you go, E? Why in the world would it be, notated by an E in these formulas? Well, who knows? Somebody came up with this idea. But it works, and I like to think, okay, it's talking about that electromotive force. So that's why they use that. And we'll talk about that in some of the formulas. We're going to get into some formulas and some math in a little bit. So resistance, this is the opposition to the movement of electrons. And it's measured in ohms. And it's measured by an ohm meter. And it is represented by a capital R, or sometimes the symbol omega, I believe. the upside down horseshoe, right? In scientific publication and formulas. So resistance, you can kind of think of it as friction, right? It's, you got a force and you've got something opposing it. So the friction that's holding it back. And it turns electrical energy into heat when the current flows. So you got current flowing, and you got resistance. Well, that's creating heat. You ever touched a wire and it seemed a little warm? That's that resistance to that current that's causing that heat. And you haven't done that. You will someday.
We did. We burnt our electrical baseboard heater. We bought a 120 volt and it should have been 240.
Ah, that would do it. That would do it. Okay. So conductors, they permit current flow. They have low resistance. And then there are insulators, which block current flow. Okay? So conductors allow that current to flow. And at the same time, you got insulators, which is going to prevent it from flowing. And we use both of those in the radio world. Conductors and insulators. So if you think about it, you think about a pipe and have water flowing through it, okay? This is a good way to it's a good analogy to understand these characteristics of current, resistance, and how they are related to electricity. So if you think about it, you've got you see my mouse moving up on there? Okay.
Why isn't Chris getting his own table?
So we've got the current flowing in this direction, right? Or the water, okay? The water's coming through the pump and it's being pumped and it's coming around this way. We got pressure, which is, hey Rick, turn off that phone. All right, so we've got pressure that's coming around here to get this water moving along, right? Now, if we think about this over as it relates to electricity, we have the current that's flowing in this direction. Okay. Now it comes from into the battery on the negative side, it's coming out on the positive side. And we've got voltage that's being applied here to keep that current flowing. So we apply voltage, and it gets those electrons just moving along, and they flow around in the as current. Now, another term that we'll use is polarity. This refers to the convention that determines which voltages are positive and which are negative. So if you're dealing with your vehicle, and all of a sudden you need to change out your battery, right? What happens if you put the negative onto the positive post and the positive onto the negative post?
You'll let the smoke on something.
Something's going to be smoking, right? Yeah. So you want to make sure the polarity is correct. And we do the same thing in the radio world. We want to make sure that we're hooking things up, the positive to the positive and the negative to the negative. And voltage from a source of electrical energy causes the current to flow. So it's the voltage that gets that current flowing. We've got a handout that has some of this stuff on it. My wife put it together. She handed it to me as I was walking out the door. So I trust that everything in there is accurate because I know what she does. Okay, so resistance is a material's opposition to the flow of current. So if you're trying to put something through you got a wire, and at the end you have an insulator, that's going to be resistance, and you're not going to be able to get that current to flow through that insulator. Okay, that's resistance. There's always opposition to that flow of current, even within that wire itself. So voltage, current, and resistance affect each other. For example, here, if you have higher voltage, it's a bigger push. It causes more current. There's more flow. So if you take your pump, and like in the water example, and you are putting more pressure to that pump, you're pushing that current or that flow of water. It's going faster through that system. All right, we got lots of practice questions tonight. So these practice questions are all questions right out of the test that we'll be having. So electrical current is measured in which of the following units? Volts, watts, ohms, or amperes? Now this is the current.
D.
D. That is correct. All right. What is the name for the flow of electrons in an electrical circuit?
D.
D again. Current. All right. What is the electrical term for the force that causes electrons to flow?
A.
A. That would be the voltage. That is correct. And which of the following describes alternating current? And we didn't talk about this too much, so this is kind of a prelude into what we're going to be talking about. So which of the following describes alternating current? Current that alternates between a positive direction and zero, current that alternates between a negative direction and zero, or a current that alternates between positive and negative directions, or all of these.
I suppose it would be all because you have to pass zero.
You do have to pass zero, that's correct.
Otherwise,
Think C.
There you go, I think it is C. Yeah. It's alternating between positive and negative directions.
otherwise you're stopping at zero.
Yep. Which instrument would you use to measure electric potential? An ammeter, a voltmeter, a wave meter, or an ohm meter? Electric potential.
D.
B. Because if you think about it, you have to apply what? You have to apply voltage to get your current to move, right? So that's where your electric potential comes in. Which instrument is used to measure electric current? An ohm meter, an electrometer, a voltmeter, or an ammeter?
E.
It is D, it's the ammeter. Yep. Okay, so we're going to talk about two kinds of current. Okay, we're going to talk about direct current, or DC. And we're going to talk about alternating current, or AC. Now, when you think about these two kinds of current, DC, what do you think about when you think about DC current? If you've ever delved into it? Batteries, yeah. Batteries are direct current. An alternating current would be what? It's what we plug into the house, right? Okay. So current that flows in only one direction is called direct current. And batteries are a common source of direct current. Right, Rick?
That's right. DC District of Columbia.
Goes in one direction. All right.
Yeah, straight to your wallet.
knew there was a reason I didn't actually
I'll
ask
walk
you
over.
that question. All right, current flow that flows in one direction and then in the opposite direction is called alternating current, or AC. And household current is a great example of alternating current. And alternating current reverses direction on a regular basis. So if you look at this over here, right, it's coming this way to the positive direction, and then it comes back down to the negative direction. It's on a regular basis, right? Almost looks like that sine wave we were talking about last week. Okay? And each process of reversing is called a cycle. So, just like we talked about last week, right? We come up here, come down, here's a cycle, right? And we do the same thing. Here's another cycle. And here's another cycle. And the number of cycles per second is frequency. Wow, measured in hertz. Well, we talked about this with radio waves last week, right? It applies also to electricity. Okay. So 1 hertz is equal to 1 cycle per second. All right. So as we talk about current flow of current, a circuit is any path through which current can flow. So you want to be able to have a circuit so your current can flow through it, right? And there are multiple ways that you can have circuits where current's going to be able to flow. And electrical circuits are made of components and connections between them. So they're different components, which we'll talk about, which some of those are capacitors, resistors, and a number of other components. And there are connections that go between those different components. And that's what makes up an electrical circuit. So if 2 or more components are connected in a circuit so that the same current must flow through all of them, that is a series circuit. Okay? So you have 2 or more components. They're connected in a circuit. You ever seen those circuit boards that are inside computers or other electronic equipment, right? They're usually green and they got places where they've been soldered, and those are circuit boards, and you have different circuits on them, and these are what make the connections through those. But if that current needs to flow through each of those components, then it is a series circuit. Now, a short circuit is a direct connection between 2 points in a circuit. So if you've got 2 points and you got a direct connection between those 2 points, that is a short circuit. Now, an open circuit is made by breaking a current path in a circuit. So if that current cannot flow from this component to this component, but there's a break in it, then you've got an open circuit. Okay? And that current will not flow through that open circuit. So this is an example of a series circuit. You have a battery, and we've got the current that's flowing in this direction, okay, coming out of the positive end of the battery, comes through R1, then goes to R2, then it goes to R3, and it comes back around back to the battery to complete the circuit, okay? So this is a closed circuit, it's a closed loop, and it's going through each of these in turn. So the same current at all points in the circuit, that's what we're seeing here. So these series circuits provide one and only one path for current to flow. It can only go one way. Okay? And it's going from each component to the next. Now there's another kind of circuit out there. As opposed to a series circuit, there is a parallel circuit. Now a parallel circuit is one where current can come through multiple directions. They actually are running in parallel. So the current comes out of the battery, comes over here. Some of it can go this way, some of it can continue on and come down this way, and some more of it can continue on and come down this way. And then it all finds its way back to the battery. Complete the circuit. This is what's known as a parallel circuit. So the same voltage at all parts of the circuit. So it has the same voltage at R1, R2, and R3. And parallel circuits provide multiple paths for the current to flow. Now I'm going to back up just to this other slide just real quick. Now the same current flows through the series, okay? So we got current here flowing through all of these circuits. But over here, we have the same voltage coming through all of these. So that's the difference between parallel and series. And where this is a red letter, that is a definition that you're going to want to remember for the test. Okay. All right. In which type of circuit is DC current the same through all components? Now we're talking about DC, which is direct current. So DC current is the same through all components. A, yep, that is the same. Okay, now in which type of circuit is voltage the same across all components? That would be B, parallel. Yep. Okay, how is a voltmeter connected to a component to measure applied voltage? We didn't have this in any of the slides, so this is something we're going to have.
I say C, sounds good.
You say C?
I like that word.
Quadrature? Okay, I'm hearing B. Is that what I'm hearing? It is B. So we're hooking up a voltmeter, right, to measure the applied voltage. So we hook that up in parallel. All right. I see some notes being taken, so I'll slow down.
She's drawing.
She's drawing. That's good. You know, you should know that, Rick. Pictures are good.
No crayons.
All right. When configured to measure current, how is a multimeter connected to a component? What do you think?
A.
A? Yeah, I think so too. All right. So multimeters. So the basic electrical test instruments are simple meters: voltmeters, ammeters, and ohm meters. Those are basically the three things that we're wanting to measure, right? So that would be a pain, right? You got to have 3 meters to measure those 3 things. So in order to avoid that, the multimeter was invented. You guys ever seen one of these? Multimeter, right? It can measure ohms. It can measure ammeters. It can measure volts. It can measure all of this stuff, all in one little unit. And so you'll want to have one of these when you're testing out your equipment.
Yes, sir.
Rick just puts this finger on this one and this finger on that one.
Especially after you think you might have experienced a short circuit.
Yeah. Where you think you may have a direct connection between 2 components?
Yeah.
Yeah. All right, so the multimeter was invented, and it's short for multifunction meter, and it measures all 3 electrical values of voltage, current, and resistance. Other names that you might hear about it is a bomb, a volt ohm meter, or a digital voltmeter. So you can have different names. Now, there are ways that these can be damaged. You have it on the wrong setting, and you put it into two things on your plug.
Jeff is speaking the truth.
I've done that back when I was young and dumb. Now I'm old and dumb.
I'm old and dumb, still do.
So, you know, there are ways that you can damage these things. Measuring the voltage of an energized circuit when the meter is set to measure resistance. So you're trying to measure voltage and you got it set for resistance. You don't want to do that, right? Exceeding the meter's voltage rating. The voltmeter and leads are not rated to use the voltages to be measured. You know, these things will melt. I guarantee you, they will melt. So you don't want to do that. From experience, I melted one once. So.
It goes down the insulation.
It does.
You also probably don't want it set to measure amps when you're measuring volts.
That is correct. You do not want to do that.
Yeah, little TV screen goes.
Yep. So there are ways that can be damaged. So here's a question for us. Which of the following can damage a multimeter? Failing to connect one of the probes to ground, attempting to measure voltage when using the resistance setting, not allowing it to warm up properly, or attempting to measure resistance using the voltage setting. So, I'm hearing C. The answer is C. So A and C are very similar, right? So attempting to measure resistance using the voltage setting, or attempting to measure voltage using the resistance setting. So you want to, when you're measuring voltage, you always want to have it on the voltage setting. Okay, which of the following measurements are made using a multimeter? Signal strength and noise. Boy, that's an important thing for radios. You want to know what that signal strength and noise is. Impedance and reactance. That's important in antennas. Voltage and resistance. Or all of these. What do you think? What do you think? C.
I wish I could do A.
Yeah. You got to have a different thing, kind of meter for that. Okay. What reading indicates that an ohm meter is connected across a large discharged capacitor? Okay, so a capacitor is an electrical component that stores energy, right? Now, when you turn off the power, there is still some energy that's stored in that capacitor. And it was really a big thing in older ages of ham radio, because the radios were made with a lot of big circuits and big components, a lot of big capacitors, and they could hold that charge for a long time after the power has been taken off. So understanding, you're trying to figure out what a discharge capacitor, what kind of reading you're getting with an ohm meter. So we've got the choices of increasing resistance with time, decreasing resistance with time, steady full-scale reading, or alternating between open and short circuits.
A.
Okay, I'm hearing A, increasing resistance with time. Let's take a look. It is A. So as your time, your capacitor is continually discharging, right? You're getting more resistance as that capacitor is being discharged. And one of the things when you get a radio, you'll have a power supply, and because if you're plugging it into your wall, your household current, you have to go through a power supply to drop that down to 12 volts, so that that's what your radio equipment runs on. So it goes through, and it will take and decrease it to 12 volts. That's the best thing to do, is have a power supply that'll do that. And when you turn that off, a lot of them have a meter. And you turn it off, and for a few seconds, that meter stays right up there at 13.8 volts. And then it slowly starts to come down as that power supply turns off. That's because there's a capacitor in there that's maintaining that current, and it's holding the charge in there. So you always want to make sure that you've got everything that discharge capacitor before you start doing anything with that. Okay, which of the following precautions should be taken when measuring in circuit resistance with an ohm meter? Ensure that the applied voltages are correct. Ensure that the circuit is not powered. Ensure that the circuit is grounded. Or ensure that the circuit is operating at the correct frequency. What do you think? B. Yeah, you don't want any power going to that, do you? So what happens if you're measuring it and you've got power going to that circuit?
Probably be buying a new meter.
You will probably be buying a new meter, and there is a chance that you might be feeling something. You don't want to feel that. Okay. Which of the following precautions should be taken when measuring high voltages with a voltmeter? Ensure that the voltmeter has very low impedance. Ensure that the voltmeter and leads are rated for use at the voltages to be measured. Ensure that the circuit is grounded through the voltmeter. And ensure that the voltmeter is set to the correct frequency. B. That's correct. Okay. Now we're going to get into some fun stuff. So, Ohm's law. And this is where we can calculate the different parts of electricity. So Ohm's law, E, what does E represent? Voltage, right? And the units are volts. The I represents current, and you measure it in amperes. What do you think the R represents?
Resistance.
Exactly. It represents resistance, and its units are ohms. Okay? So, this is a simple diagram over here in this circle that makes it an easy way to remember how to calculate the formulas. And I'm just going to check. Okay, yep, formulas are here. So to calculate resistance, R is equal to E, which is voltage, divided by current, right? Current is equal to voltage divided by resistance, and voltage is equal to current times resistance. So an easy way to figure out, if you know two of these, it's a simple algebraic equation. Everybody's had algebra? Kinda? Know your algebra? Yeah, I forget my algebra. But this will help. So if you take, let's say you know E and you know R, but you don't know I. You can hide this I, just cover it up, And then your equation is E divided by R, which is the same as I equals E divided by R. So the one that you're trying to find, just cover it up. And so if I'm trying to find out what E is, and I cover up the E, what would it be? The I times R, right? So that's an easy way to remember this. If you can remember this circle, and remember what E stands for, voltage, I stands for current, and R stands for resistance. When you're given these, you'll be given some problems that'll give you 2 of the 3. You need to solve for the third. And by remembering this circle, it makes it a lot easier to calculate that. Okay? Any questions? All right. So we're going to go through some examples. So everybody remember that circle, right? Okay. So here's our example. We've got I is equal to 2 amperes. I is what?
2 amps. Current.
Current, yes. And we got a resistor that has 10 ohms, right? And we're trying to find out what the voltage is. So, if we go back to our circle, and we're trying to find the voltage, right? What are we going to do? We're going to multiply the current by the resistance. So in this example, we got current of 2. We've got resistance of 10. What's our voltage going to be? 20 volts, right? 2 times 10 is 20. My simple mathematical mind. All right. Here we've got another one. And we don't know the current this time. So what's in the top part of that circle?
Voltage.
Voltage. So we got 12 volts, right? And so that means we're going to have 12 divided by resistance in this case, right?
Yep.
Which would give us 2 amps, right?
Yep.
Okay, I've got a couple more examples here. This is in a story problem. I always hated story problems when I was dealing with math. Until I got into the accounting world, and everything's a story problem. Okay, what is the resistance of a circuit in which a current of 3 amps flows when connected to 90 volts? So what's going to be on the top?
90.
90. It's going to be divided by
3.
3. So that equals 30 ohms, right? Okay, what is the current in a circuit with an applied voltage of 120 volts and a resistance of 80 ohms? So we're going to take, voltage is always on the top, 120. It's going to be divided by the resistance of 80, which will come out to 1.5. Okay. And what is the voltage across a 2 ohm resistor? So we're looking for voltage, so we're looking for the one that's the big E on the top, right? So we got a 2 ohm resistor, and the current is 0.5 amps. So what is that voltage going to be? It's going to be in volts, right? So we're going to take 0.5 amps times 2 ohms, and that's going to equal 1. Okay. Any questions on how these are done? Kind of straightforward, right?
Mm-hmm.
I like how they put that circle thing. I can remember that. Okay. Okay, here we go. What are the units of electrical resistance? Simons, mhos, ohms, or coulombs? See? Yeah. I haven't heard of some of these. They're probably accurate, and that probably represents something, but I'm not an electrical engineer. Okay. So why are metals generally good conductors of electricity? They have relatively high density. They have many free electrons. They have many free protons. Or all these choices are correct. What do you think? B? The answer is B. They got these free electrons blowing around there, right? In metals, and so that they can conduct that electricity. Okay, which of the following is a good electrical insulator? Copper, glass, aluminum, or mercury?
B.
B, glass? Yeah, it is. So what would copper be?
Conductor.
It'd be a conductor, wouldn't it? So, and glass, you hook up some electrical stuff to glass, what's going to happen? Right. It's not going to do it. So a lot of times you will see glass insulators. Okay, what is the formula used to calculate current in a circuit? Okay, so current is I, right? All of these have I, so we're trying to solve for I. And what's going to be on the top? E, right? So we're not going to add the two together. We're not going to subtract them, and we're not going to times voltage by resistance, are we? But we're going to divide it, right? So it would be B. Okay, what is the formula to calculate voltage in a circuit? A? Yeah, that's it. Okay. What formula is used to calculate resistance in a circuit? So remember what's on top, right? That's E. So this would be
B.
All right, now here we're going to have to apply ourselves here. What is the resistance of a circuit in which a current of 3 amps flows when connected to 90 volts? So we're looking for resistance, right? We've got current, which is I of 3, and E of 90. So the formula would be, the answer would be B. The formula is going to be 90 divided by 3, right? Okay, what is the resistance of a circuit for which the applied voltage is 12 volts and the current flow is 1.5 amperes? So we're looking for resistance. We got the volts, which is 12. And the formula would be, what do you think?
12 divided by 1.5.
12 divided by 1.5. So 12 divided by 1.5 would be
C.
You knew
I went the wrong.
that.
I think I almost liked it.
You did. Okay, what is the resistance of a circuit that draws 4 amps from a 12-volt source? So volts is E. It's on top, right? So we got 12 on the top. We've got current of 4 amps. So we got 12 divided by 4. That's going to be A. Yes, it is. Okay. What is the current in a circuit with an applied voltage of 120 volts and a resistance of 80 ohms? All right, what is the current through a 100 ohm resistor connected across 200 volts? So we've got 200 volts, that's going to be up on the top. We got the resistor of 100. So we're looking for the current, which is in amps, and it's I. So you got 200 divided by 100. It's going to be C, right? Okay. And what is the current through a 24 ohm resistor connected across 240 volts? C.
C.
It is 240 divided by 24. Is 10. And what is the voltage across a 2 ohm resistor if the current of 0.5 amperes flows through it? So we're looking for what? We're looking for voltage, which is E. So it's going to be 2 times 0.5, right? A 1 volt. I think there's a couple more. What is the voltage across a 10 ohm resistor if a current of 1 amp flows through it? So we're looking for the voltage, and we've got a 10 ohm resistor with a 10 amp current, or a 1 amp current. That would be 10 times 1. And what is the voltage across a 10 ohm resistor if a current of 2 amps flows through it? So we're looking for voltage, right? That's going to be D20. Okay. And I think this is a good time to take a break. So we've got donut holes, get up, stretch, and you get some fresh air if you want. And Ricky's going to change out the battery. Then we'll talk about some power. All right. Well, we're going to go on with some additional things. We're going to talk about power. Power is a good thing, and it's another part of the electrical component stuff that we talk about. And we see we got the same circle, except it's just a little bit different. What's different about it? The E's moved, didn't it? The E's no longer at the top. The I's in the same spot, right? But we don't. What don't we have? We don't have the R, right? So we have P, I, and E. E being voltage, right? I being current, and P standing for power. And it works exactly the same way as the other formula that we use. Okay? So power is represented by the symbol P, and it is the rate at which electrical energy is used. And it is measured in watts. Okay? So anybody ever heard of watts before? All right.
It's a suburb of California.
It is a suburb of Los Angeles. Yes. They had riots there. Long time
I
ago.
was gonna say it's referenced by something else, but it ends in TS.
All right. So a device that consumes or dissipates power is referred to as a load. Okay. So if we look over here on this counter, okay, we have anything over there that is going to consume power. What do you think?
Yep, coffee maker and a microwave.
What was that?
Coffee maker and a microwave.
Coffee maker and a microwave. Yes, and a refrigerator. All of which are a load, right? Okay. So that's using up power. So the formulas, just like when we were talking about volts, resistance, and current, same type of thing. Power, if we trying to find power, we hide power, right? It'd be I times E. If we're trying to find E, it'd be P divided by R. And if we're trying to find I, it'd be P divided by E. Okay, makes sense? Yeah, very, very similar, right? Which makes it easier. As long as you remember which things go on the top and which two go on the bottom. Makes these formulas pretty straightforward. So here's an example. How much power is delivered by a voltage of 13.8 volts DC and a current of 10 amps? So we're trying to find power, right? Power's on the top. So we got voltage times current. Or current times voltage, either way. So we got P equals voltage times current, which is 13.8 volts times 10 amps, is 138 watts. Okay, so that is how much power is delivered by this battery at 13.8 volts and a current of 10 amps. This 13.8 volts, you're going to see that a lot when you're dealing with batteries and amateur radio. Okay? Because that's what a radio is going to require. It's going to require a voltage of 13.8 volts. What happens, Rick, when you have a battery that's only delivering you 10 volts?
Nothing.
It will, but it can damage internals.
It can damage the internal
Quick
parts of that radio. So you always want to make sure you have a battery that's delivering your 13.8 volts. And if you ever have a question, you can always test it with this.
Even on like handhelds, 13.8.
Mm-hmm.
Yeah.
Yep. Okay, how much current is required to deliver 120 watts at a voltage of 12 volts direct current? So we're trying to find current in this situation, right? So we got power on the top, which is 120 watts. We're going to divide it by 12 volts. So 120 divided by 12 is 10, right? All right. So electrical power is measured in which of the following units? Volts, watts, watt hours, or amperes? Watts. That would be B. Yes. All right. Which term describes the rate at which electrical energy is used? Okay, we're using up the electrical energy, right? What term? What are we using? What do you think?
C.
C.
Power.
Power. Yes, that is correct. Okay, what is the formula used to calculate electrical power in a DC circuit? So P is the right one, right? And what's on P's on the top? So what are we going to do with the 2 on the bottom? Times them together. So it's going to be A, right? Okay, how much power is delivered by a voltage of 13.8 volts DC and a current of 10 amps? I think we had this in an example. A. 138 watts. How much power is delivered by a voltage of 12 volts DC and a current of 2.5 amps? What do you think? So it's going to come out in watts, right? Because it's power. So we got 12. Power's on the top, so we're going to be timesing these two together, right? 12 times 2.5 is equal to B. Yep. And how much current is required to deliver 120 watts at a voltage of 12 volts DC? So current's going to be in amperes, right? We got the power on the top, which is what, 120. It's going to be divided by 12 equals B. Okay, so we're going to start talking a little bit about components and units. Okay, components in electrical circuits perform functions such as storing or using energy, routing current, or amplifying signals. All of these things we will use in amateur radio. We're going to be storing or using energy. What stores or uses energy? What stores energy?
Batteries.
Batteries, yes. What uses energy?
My brain.
Yeah. What uses energy?
Components.
Components, yeah. And routing current, amplifying signals, all these things we'll be dealing with. The three most basic types of electronic components are resistors, capacitors, and inductors. Okay? So these are the basic components that we're going to be dealing with. We're going to be dealing with resistors, capacitors, and inductors. And we could use actual drawings to show how components are arranged in circuits, but this would be too cumbersome for most circuitry. Instead, we use schematic diagrams. Okay? Yeah, you could draw everything out, right? But you'd be drawing lots of pictures. Perfect for Rick. He likes pictures.
I got a red crayon.
But we'll use schematic drawings. And this is a schematic drawing, okay? And we're going to talk more about these later, but this represents the different components in a circuit. This is a power supply, okay? And these are resistors here. We got some resistors. We got a transformer. We've got a switch. Okay, so there's a lot of different things. This is a symbol for a ground. All these are symbols for grounds. So, but we'll talk more about those schematics as we get going. So let's start with resistors. So what does a resistor do? It restricts the flow of current. You know, just as you think about a valve on a water line, right? It restricts the flow through that pipe. So if you want to stop the water going through a pipe, what do?
Shut it off.
Turn it off, right? Shut the valve. Same thing as what a resistor does to the flow of current. It stops it.
Some folks will refer to a resistor as a restrictor.
They will.
Don't watch that. Some people call it a restrictor.
So resistance is measured in ohms. And we remember Ohm's law, right? Where we have E on the top and I and R. And we're talking about the R piece of that formula. And that's what a resistor is measured in. It measured it in resistance, it's measured in the ohms. Okay. So schematic, this is a resistor schematic, and the arrow indicates an adjustable value such as for a volume control. So this is a potentiometer or a pot, okay? So you can adjust this and you can change your volume. Your volume switch on your radio is dealing with resistors. Dealing with the flow of current. And that's what causes it your volume to go up and down. And it's coming through a resistor. And this is kind of what they look like. And they're just, they can be small, they can be large. Just depends on what kind of circuitry you're working with. So here's a large variety of resistors. They can have some different shapes, but you'll have labels on them so that you know what they are. Some of them are color-coded. This is color-coded in black and white. It's because it's a black and white picture. But the one before was colored. We see we got orange, different types of color coding, which indicates a different, I'm not exactly sure what they are,
I don't remember.
but they definitely give information in regards to that resistor. Then we also have capacitors. So the function of a capacitor is to store electrical energy, and this is called capacitance. Okay? So capacitance is the storage of energy in a capacitor. Now, here's a schematic of some capacitors. Not exactly sure what kind they are, but these are different schematics of capacitors. There will be some questions on the test in regards to some of these schematics, but we'll talk about those when we get to them and what those symbols are. They're not, once you look at them and you see them, they're pretty easy to recognize. So capacitors act like a battery. So you're putting energy into a capacitor, and it's going to store that energy. And so that it stores the energy in an electrical field created by voltage between the electrodes. So here's your electrodes, right? You got two electrodes here. You got this area in between these electrodes, and that's where this energy is stored, because this is an electrical field in between these two electrodes. And it has dielectric material in between them, and insulating material in between them. So these are insulated against each other with some dielectric material inside. So they do act like a battery. This is what a capacitor looks like. And they've got different size capacitors, different colored capacitors, and they're interesting to work with. So they store electrical energy in the electric field created by a voltage between two conducting surfaces or electrodes. So you got two conducting surfaces, and you got voltage between these two surfaces, and that creates that electric field. And then the electrodes are separated by an insulator or dielectric. And as we store that energy this way when we store it this way, it's called capacitance, and it's measured in farads. Capital F, farads. So this is some examples of different capacitors. You got some bigger ones, you got some little tiny ones, and they all form that same purpose. So if we look at this one right here, we have the electrodes coming here, and we got dielectric in between them, and this is where the energy is stored. Now we've got an inductor. So an inductor, the function of that inductor is to store energy in the magnetic field created by a current flowing in a wire. So if we think about it, as current flows in that wire, it's creating a magnetic field. If you've ever thought of your alternator on your vehicle, right? It's an electrical magnetic field that's created as that current flows through the wires that are around that, creating that alternator. Same type of thing. So this is called inductance. When we're storing this energy in the magnetic field, it's called inductance, and it's measured by henries. Now, they came up with henries because some guy named Henry. He's the one that found it, discovered it, and so it's capital H. And it's made from wire wound in a coil and sometimes around a core of magnetic material that concentrates the magnetic energy. Okay, so this is an inductor. So it's made up of wire wound in a coil, and sometimes you have a core of magnetic material that concentrates that magnetic energy. So it's a concentrator. And so this is the schematic for a inductor. And this is a picture. So we got some magnetic material here, and the wire is wrapped around it, right? Creating a magnetic field. And here you've got a coil of wire that you got energy, or you've got current flowing through this, and this creates a magnetic field where energy gets stored. So that is the inductor. Then we also have variable components. And all three types of basic components are also available as adjustable or variable models. So you can have an adjustable inductor, you can have an adjustable capacitor, you can have an adjustable resistor. And this one over here looks to be a resistor, which would probably be a volume switch. Okay. So you can have all kinds of variable components. And this switch makes that radio have the ability to work. So a variable resistor is also called a potentiometer, frequently used to adjust the volume or the potential, such as for a volume control. Okay. Now another component that we have is a transformer. And transformers are made from two or more inductors that share their stored energy. And it allows energy to be transferred from one inductor to another while changing the combination of voltage and current. So if you think about it, you've got energy that needs to be transferred. And you want it to go from one inductor to a different inductor. And you might be changing your current. You might be changing your voltage. So you're transforming it. So you're changing something. Transforming, you know, if you think of the show, what is it? Transformers? What does it do? Take cars and make them into robots, or the other way around, or something, right? It transforms and changes it to something a little bit different. Same type of thing. You know, this time you're doing it with energy. You're changing it from one inductor to another. So an example here is a transformer is used to transfer energy from household 120 volt alternating current to a lower voltage for other uses, such as in electronic equipment. So we got 120 volts alternating current coming out of the plugs, right? I want to use that to power my radio. Well, I can only have direct current. I need to change it to direct current, and I need to change it to 13.8 volts. So it runs basically through a transformer. So my power supply that I use is essentially a transformer, taking it from household current down to direct current that can be used to power my radio. So that's what a transformer does. It changes things. You have the same type of thing with your computers, right? It goes through a brick, usually, right? Or some kind. This one has one right on the edge of the plug, but that transforms it so that it will not fry the computer. What would happen if I just plugged the computer directly into 120 volts? Fireworks, right.
Starts to stink.
Yeah, starts to stink, yes. Okay, so this is a schematic here for a transformer. Okay, you're transforming it from one to the other, and this is a picture of a transformer. Looks like an old transformer too, based on the picture. All right, let's hit a few practice questions here. So what describes the ability to store energy in an electric field? Okay, D, capacitance, right? So we're talking about an electric field here, right? And that goes, electric fields use what? Capacitors. And so then you're using capacitance. Okay, what is the unit of capacitance? A, yeah, the farad. What describes the ability to store energy in a magnetic field? D, inductance, right? Yes, that is correct. And what is the unit of inductance?
Henry.
Henry, yes. Okay. What electrical component opposes the flow of current in a DC circuit?
A restrictor.
A restrictor or a resistor, right? B. Okay, what type of component is often used as an adjustable volume control? C, yeah, potentiometer. And what electrical parameter is controlled by a potentiometer?
B.
That is correct, it is resistance, yes. All right, and what electrical component stores energy in an electrical field? So we're talking about electrical components here, and we're talking about an electric field.
C.
I'm hearing C,
B.
I'm hearing
B.
B. Yeah, it is B. It's a capacitor. Because capacitors and capacitance relate with electric fields. Inductors relate to magnetic fields. Okay, what type of electrical component consists of a conductive surfaces separated by an insulator?
D.
The capacitor is correct. And what type of electrical component stores energy in a magnetic field?
C.
C, and it would be the inductor. And what electrical component is typically constructed of a coil of wire? The inductor. And what component changes 120 volt AC power to a lower AC voltage for other uses?
Optimus Prime.
What was that?
Optimus Prime. Transformer.
Transformer. There we go. Yeah, it's a transformer. Okay. So we'll cover reactance and impedance, and that's probably as far as we'll get this evening. So these are a couple more terms. So in a resistor, AC voltages and currents are exactly in step or in phase. In capacitors and inductors, voltage and current have a phase difference. Okay? So we're talking here in a resistor, voltages and currents are exactly in step or they're in phase. And capacitors and inductors, voltage and currents have a phase difference. And capacitors and inductors store energy rather than dissipating it like resistors. So if we think about it, a resistor does what? It dissipates that energy, right? But a capacitor and inductor, they store it. So the things that are dissipating or resisting, they're in step or in phase, but the ones that are storing it, they have a phase difference. Energy storage creates an effect called reactance, which is the symbol X, that acts like a resistance in opposing the flow of AC current. Now, capacitors create capacitive reactance. So capacitor as reactions. So reactance here acts like a resistance in opposing the flow of the current. Now capacitors, they have capacitive reactance. Inductors create inductive reactance. So it's X subscript C. Now inductors are X subscript L. And the effects of each are complementary. So they're complements of each other. And the combination of resistance and reactance, R and X, is called impedance, represented by the symbol Z. Now, I don't know about you, but this stuff's getting confusing. Anybody getting confused?
Mm-hmm.
Okay, I want to make sure that I'm confusing you all.
Not me, I was asleep.
Yes. And so impedance represents the circuit's opposition to both alternating current and direct current. So impedance is pushing the current back, okay? And so when we have a combination of resistance and reactance, we have impedance, and it's the opposition of both AC and DC currents. And radio circuits almost always have both resistance and reactance, so impedance is often used as a general term to mean the circuit's opposition to AC current flow. Okay. This is the most important thing to remember here, is in radio circuits, they have both resistance and reactance. So they have impedance. And they often, we just use it as a general term, that it's the opposition to the circuit's flow of current. Okay. This will become clearer as we go through some questions and what they're looking for. So it's not like you got to memorize this stuff to become an electrical engineer. You don't. Okay. And with that, we'll hit a few practice questions here. The unit of impedance is, what do you think? We've hit the volt, we've hit the ampere, and we've hit the ohm.
Oh,
It's the ohm, right? Because impedance is what? Resistance, right? What is impedance? The opposition to AC current flow, the inverse of resistance, the Q or quality factor of a component, or the power handling capability of a component.
A.
It is correct. And I don't want to confuse anybody anymore by going into resonance tonight. We'll hit that next week. Any questions?
What's resonance?
Cliffhanger. Now, my better half is right here,
Oh,
and she can hand out her homework. We just came to a stopping point here.
really?
Yeah. I don't want to go into resonance tonight because we're already starting to lose my mind.
Yeah.
Too late.
But you already talked about this topic?
We did. We went through
Okay.
Ohm's law for both power and
Oh, okay.
electrical
So
currents.
they'll just take one and pass it down. Okay. So I don't need to explain any more about
Nope.
it?
And I did not go over that.
Oh, okay.